Welcome to The Explainer. Today, we are diving into the story of one single element, the one that, quite literally, forms the backbone of every living thing on our planet. Yep, we're talking about carbon.
To really get a handle on the huge world of organic chemistry, everything from plastics to proteins, we have to start with a pretty basic question. Why carbon? What's so special about it?
Believe it or not, the entire story starts with this one number, 6. That's carbon's atomic number. It means a carbon atom has 6 protons and, more importantly for our story, 6 electrons. And those 6 electrons, well, they create a bit of a predicament.
See, this problem is all about stability. For an atom, being stable is the name of the game, and carbon's electron setup puts it in a really awkward spot.
Okay, let's break this down. Like a lot of elements, carbon has this goal of getting a full outer shell of 8 electrons. It's called the octet rule. But it only has 4, so it's perfectly in the middle, halfway to empty and halfway to full.
And that puts it in a real bind. I mean, it could try to grab 4 electrons from other atoms, but its nucleus is just too small. It doesn't have the pull to hang on to 10 electrons. So what about the other option, giving away its 4 electrons? Well, that would take a huge amount of energy. So neither of those are good options. So if carbon can't steal electrons and it can't really give them away, what's it supposed to do? Well, it comes up with a solution that is just brilliantly simple. It decides to share.
This sharing strategy is what we call covalent bonding. You can think of it like a chemical handshake. 2 atoms each contribute an electron to a shared pool, and by doing that, both of them get to count those shared electrons toward their stable goal of 8.
To see how this works, just look at the simplest example there is, hydrogen. Each hydrogen atom has 1 electron. So they get together, they share their electrons, and now each one feels like it has a full shell of 2. They form a nice, stable hydrogen molecule.
And it's the exact same idea with chlorine. A chlorine atom has 7 electrons in its outer shell, so it just needs 1 more to be happy. So 2 of them get together, share 1 electron each, and boom, they both get to complete their set of 8.
And this brings us right back to carbon and how it solves its big problem. It needs 4 electrons, right? So it just makes 4 of these covalent bonds. Here, you can see it sharing with 4 hydrogen atoms, creating methane. And just like that, you have a perfectly stable and happy molecule.
Now, this simple trick of sharing 4 times is what unlocks carbon's incredible versatility. It's not just a solution. It's what gives this element a set of chemical superpowers that make it the ultimate building block of life.
So here's what you really need to know. First, it can form 4 strong bonds, which we call tetravalency. But the real showstopper, the thing that makes carbon so special, is catenation. That's its unique ability to form strong bonds with other carbon atoms, creating these endless chains, branches, and rings. And this ability to arrange itself in all these different structures leads to a really fascinating property called allotropy. It just means that the very same element can show up in completely different physical forms.
And this slide is the perfect example of that power. You take those exact same carbon atoms, arrange them in a super rigid 3D structure, and you get diamond, the hardest natural thing we know of. But then you take those same atoms and arrange them in flat, slippery sheets, and you get graphite, the stuff in your pencil. It's just amazing. Same atoms, totally different materials. Okay, so now that we've seen how carbon builds things, let's meet the simplest family of organic compounds it creates, the hydrocarbons. As the name suggests, they're just made of hydrogen and carbon.
Hydrocarbons really come in 2 main flavors. First, you've got the saturated ones. In these, every carbon atom is holding onto as many hydrogens as it possibly can, and all the carbons are connected by single bonds. Then you have the unsaturated kind, which have more complex double or even triple bonds between the carbons.
The alkanes you see here are just the classic example of a saturated hydrocarbon family. They form what's called a homologous series, which just means each member is a really predictable step up from the last one. You just add 1 more carbon and 2 more hydrogens to get the next one down the list.
So, okay, why does any of this chemistry stuff actually matter? Well, because these basic principles are what make the modern world go round. Carbon is quietly doing its thing all around us. Just think about the gas in your stove. That's mostly methane. When you light it, it burns, right? That process is called combustion. The stable bonds inside that methane break and reform with oxygen, and all that stored energy is released as the heat and light that cooks your food. Or how about soap? How does that even work? It's pretty genius, actually. A soap molecule is basically a long carbon chain with a special head. That long tail loves oil and grease but hates water. The head, on the other hand, loves water. So the tails dive into the greasy dirt and the heads stick out, forming these tiny little cages called micelles that trap the dirt inside. Then the water comes along and just washes the whole cage away. And it all works because of that long carbon chain.
So, from the simplest chemical bond to the most complex forms of life, it really all comes back to this one element's incredible ability to connect, with itself and with other elements, forming the amazing, diverse world that we see all around us.
Which kind of leaves us with one final thought. We've used this element to build our own bodies and our entire civilization. So the real question now is, as we get better and better at understanding these fundamental building blocks, what are we going to build with them next?